Hello, I'm Frederic. I'm a postdoc at Stanford University. This talk is about a joint work with Sitan, Ankur, and Morris, and it's about Kalman filtering with adversarial corruptions. Okay, so let me tell you a bit about this. First, and perhaps the most important thing you should take away from this talk is at least what is a Kalman filter, because this is a really important thing. Okay? And the story of the Kalman filter actually starts before Kalman, even in the 1940s with Norbert Wiener. And Norbert Wiener was a very interdisciplinary mathematician. And during World War II, he became interested in this problem that was very relevant to the war. And the problem was, given noisy observations of the position of a moving object, to accurately estimate its position and velocity. Okay? And to do this, he basically developed the mathematical theory behind this thing called the Wiener filter, which is a special case of the Kalman filter, and which is described in this textbook, Extrapolation, Interpolation, and Smoothing of Stationary Time Series. Okay? And why did he want to do this? It's because what they wanted to do is build a machine that, while looking at an airplane, can figure out where it's going to be in the future. The reason is that when you're building like aiming your anti-aircraft gun, because airplanes move very quickly, you need to incorporate, the fact that between firing the gun and the projectile getting where it needs to be, the airplane is going to move. And to project where the airplane is going to be, you exactly need its position and velocity. So there was a very practical, real-world thing which led to the development of the Wiener filter. And to visualize this, these are some nice plots from the Wikipedia page on Kalman filtering. And it's illustrating essentially this application in the one-dimensional setting. So on the left, we have the position. On the right, we have the velocity. Now, the red, that's the input. So that's a noisy observation of the position, like you would get maybe with a radar signal. And the black, in both cases, is the ground truth position, and on the right, it's the ground truth velocity. And what you would like to do is basically optimally denoise the input so that you get a much better estimate of the position and the velocity of the particle. And you can see in these examples, the Kalman filter output is the green line. Indeed, for the case of position, it's much more accurate than the ground truth inputs. And on the right-hand side, we see that the Kalman filter is also able to produce a high-quality estimate of the velocity of the particle, just like you would need, for example, in the anti-aircraft fire example. Okay, so that's a bit about the Kalman filter. Now let's set the stage a little bit more formally, mathematically. What exactly is the mathematical model here? It's a linear dynamical system. Because, for example, a moving particle, you can think it's taking position and adding its velocity or something, so that's a linear update. And in much more generality, the assumption is that there's a dynamics, which is known, where at each time the state of the system xt is given by a linear function of its previous state plus some kind of disturbance. Okay, so in the Kalman filter, we assume that this disturbance is Gaussian and it's independent at each time. And what we get is we don't get to see the system directly. So instead, we only get to see a noisy observation of the model. And again, we consider a general linear function, b, of x to be the observation at time t, and we add some noise to make it realistic. And again, the noise ut is assumed to be Gaussian. And in the particular case we were talking about before, xt is the state of the dynamical system. It's the position and velocity of the projectile or airplane. And yt is a noisy measurement of the position. So note that yt is not an observation of the entire state directly, because the state also includes the velocity. But it's the position, and by observing the position over many rounds, you were able to figure out what the velocity is, more or less. And finally, why is there noise in the model? Well, the reason they put noise into the model, at least in the case of the airplane, is because the airplane is not just going to fly straight at every time step, but its velocity is going to change and it's also going to turn. And so the noise was introduced as a statistical model of that phenomena. And in general, that's the purpose of the noise, is to allow for the dynamical system to do interesting things. Okay, so this is the model. Now, what is a Kalman filter? So the Kalman filter is the optimal estimate of the state, xt, from the observations y1 to yt minus 1, okay? In general, the Kalman filter is the optimal estimate of the state from whatever observations are appropriate. So this would be the so-called causal Kalman filter because it's looking at the past and is estimating the current state, but there's many variants of that and they're all basically would be known under the name of the Kalman filter. Okay. Now, an interesting historical tidbit is that although the Wiener filter, the special case of the Kalman filter, basically for the aircraft problem, was developed for a very real-world problem. At the time, it was a bit ahead of the time, so it was not actually deployed in World War II. Then when Kalman came up with the Kalman filter, however, it was perfectly timed and it played an important role in the success of the Apollo space program. Okay, and now, of course, Kalman filter has infinitely many applications. Now, finally, one other context you might have heard of the Kalman filter, that's very related, is in control theory. Suffice to say, if you want to optimally control a linear dynamical system in the classical LQG model, the Kalman filter is half of the optimal controller, and this is due to something called the separation principle. So it's not really important to know what that means, just that that's one of the important applications of the Kalman filter. And for the rest of the talk, we're not going to worry about control theory, but we're going to focus on just this half, the Kalman filter. Now, Kalman filter is amazing, but as observed by many, many authors over the years, it does have some limitations. And I really like this description in this abstract by Schick and Mitter. It basically says, well, if the data satisfies the assumption of normality, then the Kalman filter is extremely good and it's extremely useful. On the other hand, if you have non-normal noise, and in particular, if you have outliers, we know that this really degrades the performance of the Kalman filter and leads to lots of potential problems, okay? And so the challenge that we'll be interested in for this talk is how to build a Kalman filter which is more robust to outliers. Now, first, we should understand why is a Kalman filter not so robust to outliers. And on the right, I wrote down basically the Kalman filter equations. Now, they might look very complicated. They're actually conceptually pretty simple once you go through all the notation. But all you need to observe from these equations is that the forecast, the output of the Kalman filter, which is x hat t given t minus 1 in my notation, is basically a linear combination of the past observations y1 through yt minus 1. Okay? And it makes sense because it's the optimal estimator for a problem where everything is Gaussian. And if you have a little bit of experience with Gaussians, you know that the optimal everything in Gaussian space is going to be a linear function. But this linearity is good because it's optimal in the Gaussian setting, but it's really bad for robustness because if you take a single one of the observations and send the size of it to infinity, basically the output of the filter will blow up, okay? So if I even have one outlier, you can totally ruin the output of the Kalman filter. And in the terminology of robust statistics, I would say that this filter has a breakdown point of 0%. Okay, so this is basically the least robust possible estimator. Now, this is not just a theoretical problem, but a real problem that occurs when you apply the Kalman filter. So there are many possible or proposed solutions. The thing that they all have in common is that they are nonlinear. And let me just tell you about a few of the ways that people in practice can try to fix the undesirable behavior of the Kalman filter. One, which if you're familiar with robust statistics, might be the one that you would try, is you can kind of rederive the Kalman filter, but instead of using the squared loss everywhere, replace it with Huber loss or L1 loss, which are classical and sort of more robust losses than the squared loss. Okay, so that's certainly one option. Another option, possibly even more popular, very natural if you're familiar with the Kalman filter, is that the Kalman filter itself has basically some kind of confidence intervals inside of it. And so you can use those confidence intervals to delete updates which appear to be too large to be statistically plausible. Okay, so that's kind of a natural engineering solution based on the Kalman filter. Now in the paper of Schick and Mitter, which I just mentioned, what they do is they derived some kind of optimal filter, but it required to have basically very few corruptions. So it was in the limit as the number of corruptions goes to 0, and they did a Taylor expansion. And also they required to know the contamination model. So basically know how the noise is non-Gaussian. And so it was a bit limited. But that's actually one of the main theoretical results in this area. And beyond that, although there's many things that people have tried, based on practical motivations, there's not very much theoretical guarantee. Okay, and maybe it's a bit surprising, so I just wanted to say a bit, why are there not really many theoretical guarantees in this area? Like we said, there's many reasonable ways that you can try to make the Kalman filter more robust, and you can, of course, implement and check them in simulations. On the other hand, we have a lot of theory for other problems in robust statistics, like robust mean estimation. And in particular, for 1D robust mean estimation, we have a great understanding of the Huber minimizer of the Huber loss, or as the minimizer of the L1 loss, which would be the median. And we know those are quite robust in the appropriate setting and with appropriate assumptions. And so what I want to tell you is that you cannot just read those papers and, oh, okay, now I know how to understand like Huber regression. I'll apply that to the Kalman filter. It's not going to be that easy. And here is perhaps the main reason is that Kalman filtering, fundamentally the number of observations, or you can think samples, is directly linked to the complexity of what you want to estimate, which is the whole trajectory. Okay, so you don't have the situation where you have a fixed parameter like the mean and you take the number of samples to infinity. It's just not like that in Kalman filtering. And that is the main reason I think that you will run into trouble just trying to adopt theory for mean estimation to this problem. The second reason, which will show up a lot if you try to construct an online estimator like the Kalman filter directly. In particular, this happens, this is an issue when you try to analyze the modifications of the Kalman filter I discussed on the previous slide, is that the Kalman filter ends up to be nice to analyze because it is a linear dynamical system itself. On the other hand, we know for robustness we need nonlinearities, and this creates some kind of dynamical system which is much more difficult to analyze. And finally, and related to the reason 1 above, even the exact formulation of the problem is a bit subtle, because in mean estimation, when there's no corruptions and you have enough data, you can always recover the mean. But for Kalman filtering, even without the contaminations you saw in the example, we don't exactly recover the trajectory. We just want to recover the trajectory as best possible given the data. Okay, so now I want to discuss the precise model. I just said it's a bit subtle. So for the observations, we use a standard Huber contamination model. This is the same as in the paper of Schick and Mitter. So for every round, you'll flip a coin with probability eta. That round is corrupted. And we'll record this in this random variable a star I, which is not observed by the algorithm. And now we can define what the goal of our algorithm is. With a bit of thought, what we came up with is what you want to do is compete with the Oracle Kalman filter. And what is the Oracle Kalman filter? It's the filter which gets to know which rounds are corrupted. Okay, and why is that good? Is because if you know what rounds are corrupted, you'll just ignore them. And it turns out that the solution to that problem, where basically random observations are dropped, is called, that problem is called Kalman filtering with intermittent observations, and the Kalman filter for a slightly different dynamical system is the optimal solution to this problem. Okay, so that's good to know that there's, at least this is one possible benchmark we can try to compete with. And the point of picking that benchmark, first of all, it's sort of better than anything we could possibly do because we don't know which rounds are corrupted. And that benchmark, that Oracle common filter, optimizes a simple objective, which is clean posterior likelihood. Okay, and so we'll consider that our objective, and our goal will be to find a near maximizer of this function. And it's just some very reasonable function that is basically trying to fit the observations on the clean rounds, and also takes into account the prior so that it doesn't want to take very large steps in each round. Okay, so that's explicitly the functional. We want to get a near maximizer of this. It's an unknown function because we don't know which rounds are corrupted. Now another thing that we'll do is we'll move to the offline setting. So like I was saying, there's many variants of the Kalman filter. Before I was emphasizing the online or causal filter, but closely related is something called the Kalman smoother, which is a offline filter that estimates the state at time t given the past, present, and future. Okay, so those are both important in their own right. And what we'll do is we'll actually focus on the offline setting. This allows us to avoid some of the difficulties I mentioned with understanding a nonlinear dynamical system, and we'll do some kind of reduction-based argument to get some online results. And I won't say much about the reduction except that it uses the stability of the Kalman filter, and it's a little bit inspired by the techniques in that literature and in the paper by Schick and Mitter. Okay, so we're going to focus on building an offline filter, or a smoother. And this is roughly the idea for how our smoother works. We're basically going to solve a very large optimization problem. And naturally, the optimization program has variables which correspond to whether a round is corrupted or not. Okay? And the objective, once we have those variables, it's natural to just plug those in as a replacement for the true indicators of which rounds are corrupted. And that's the objective that the program will try to optimize. And we will try to optimize over the trajectory, which is the x hats with steps w hats. And the trajectory should satisfy the dynamics, and we will also put further constraints which are satisfied with high probability by the ground truth. And the choice of those other constraints will be very important to make the program actually work. And I won't say much about this, but since we have 0, 1 variables, we need to use sum of squares and be a bit careful to make this into an actual algorithm. But that's what we do, so we use a degree 4 sum of squares relaxation. Okay, now I want to discuss just a bit about the proof idea. So we're going to use 2 standard assumptions from the control theory literature. One will be uniform stability, which is saying that if I power the matrix A many times, it does not blow up. An important part about this version of the assumption is that it allows for unit eigenvalues. So this assumption will not, generally speaking, blow up as the eigenvalues approach the unit disk, the boundary of the unit disk. And this is the same assumption made in the stability of the Kalman filter literature and in Schick and Mitter's paper. And also the very classical assumption of observability, which is just saying that the measurements actually do provide for a meaningful estimate of the state. And what it's saying is that, say there's no noise, and I get all of the observations, up to say time s, I should actually be able to solve the corresponding linear system and get the state x0. So it's a condition that this linear system corresponding to the observations is actually full rank. And this observability assumption is going to play an important and slightly complex role in our analysis, because when we have the contamination, it's going to be kind of like the leading rows of this linear system, and in general that's going to break the full rank property of the system. And this is going to cause a lot of the challenge for our analysis. And in this one slide, I'm trying to summarize how this actually plays into our analysis. So first of all, on the first line, we have the assumption. So I just wrote out the appropriate quantitative version of the observability assumption. So this is saying the bottom singular value of that matrix is lower bounded by some constant kappa. Now, like I said, we're going to be basically deleting some rows of the linear system. And this corresponds to looking at this subsampled system where we only get most of the terms in that sum. And by matrix concentration, this will be lower bounded by its expectation, which is lower bounded by 1 minus eta times kappa I minus a deviation term. And the key thing that arises by considering this matrix concentration is we understand that large eigendirections are going to be well preserved by the subsampling procedure. And what this is going to say is that even though we have contamination, at least if we know which rounds are corrupted, we do actually get a good idea of the state in certain directions, in the large eigendirections of the observability matrix. And then the challenge will be to deal with the small eigendirections, which can be swamped by the deviation term. And then just to summarize the idea to handle those very briefly, what happens is it's just not possible for the system to have this small and not well observable part that stays a significant component of the state for a long time. If you put together all of the assumptions of the dynamics, the stability, and observability, you either will need to be able to actually figure out what's going on in this poorly observed direction, or what's happening in that direction will actually provably shrink and become small, so it's not an issue that you don't see it. Okay. So please see the paper if you're interested in more about this, but that's kind of the key technical idea in our paper, summarized very quickly. And we'll use the fact that PSD constraint is convex, so we can enforce it with the AJs, the program variables, replacing the A star Js. And then we'll construct a sum of squares proof, which expresses the idea I just said. And that's more or less how we end up with this theorem. Okay, so this is the main theorem of the paper. And it's saying that we can indeed build a version of the Kalman smoother whose performance kind of degrade naturally as eta goes to 0. And this is with the observability and uniform stability assumption that I just mentioned. And also, if you see the paper, we have, like I said, a reduction that gives some kind of similar result in the online setting. Okay, so that, in short, was what we did. There are a lot of interesting and important future directions to go. So first of all, the sum of squares, we use only degree 4, but still, even with degree 4, that makes it quite hard to implement. So that's an important direction, is to find a faster and more practical algorithm. If you make very strong assumptions, it is possible to get simpler algorithms to work, but basically under the general and interesting situations of general interest, it seems like future further work is going to be needed. And also, if you looked at our theorem statement, you'll kind of see that there's a constant which depends on a bunch of system parameters like the condition number, or the lower bound on the observability matrix that I mentioned with the kappa. And it was really important, I think, to understand the fundamental information theoretic limits here. And even in the intermittent filtering setting where you don't have corruption, you just have lost observations, turns out what happened is a bit subtle, and it was worked out in this paper by Mo and Sinopoli. And so basically for unstable systems, the breakdown point is actually less than 1/2, and they gave a formula for the breakdown point. So even in simple settings, what happens in general beyond, for example, in the unstable setting is very interesting. And it would be really great to have a good understanding of the correct behavior in the more challenging contaminated setting. Okay, so there's lots of interesting future directions, but we think that our work is a good first step to understanding robust Kalman filtering. All right, thanks for coming to my talk, and hope to talk to you sometime in person. Thanks.